Assignment 20, question 13. And in this case here, you're given a number of molecules and asked to state the hybridization of each carbon atom. This is going back to first semester, the stuff you're reminded about in class or online courses if you're looking through the notes and following along with Captain McTaggart. But what hybridization is. Now, the important ones for carbon, we're either going to have, write that up here, just as kind of a refresher, sp3. You want to think you need, say, 4 electron groups. sp2 if you have 3 electron groups. sp if you have 2 electron groups. If you don't remember anything about hybridization, at least remember that portion up there. And what we mean by an electron group, and think about kind of that area in space that's needed to be occupied by something, either an atom or a lone pair. So looking at this first one right here, each carbon, let's start right here with this carbon. This carbon is bound to 3 things. Okay, so it has 2 hydrogens sticking off, those are taking up space, and then it also has this double bond to this carbon. This counts as 1 electron group. So there are 3 areas of space that are needed around here. That means you're mixing 3 of its main valence orbitals together to get 3 hybrid orbitals. So that's where we're getting these sp whatever, sp numbers. So you start by mixing an s, and then however many more you need. So if we need to have 3 total, s is 1, p, and p. That's how you get sp2. So in this case here, this carbon is an sp2. This one right here has 2 electron groups bound to it. You have this carbon atom sticking off on this side, this carbon atom sticking off on this side. So in terms of geometry, this is linear. Right? There's only 2 things coming off of it. So according to Vesper, they're going to be 180 degrees to each other. 2 electron groups total. We're not counting how many bonds necessarily are involved here. It's more areas of space. So that means mixing 2 things together. So 1, 2, sp. So this one is sp hybridized and linear. This one here would be trigonal planar, 3 areas of space. Over here, you have a double bond, single, single, so 3 things. Also, sp2. Now, all of these 3 over here are all the same. Each carbon has 4 bonds to it, or 4 different atoms or groups attached to it. So it's written out in such a way that's all stuck together, but you know there's 2 hydrogens also on this carbon, right? So 1 up, 1 down here. The 4 things sticking off of it, so it means 4 areas of space, 4 electron groups. So then it's going to be sp3, s, p, 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 to get up to 4. So sp3 for all of these ones right there. Remember your Vesper, sp3 should be tetrahedral. That's how you get everything to spread apart as far as possible from each other to reduce all those electronic repulsions. You're going to get that geometry. But down here in B, it's going to be really similar, right? So B, just like this one here, identical, will be sp2, 3 electron groups. This guy here too, 3 electron groups, right? 1, 2, 3. This one, 2. This one, 2. That one, 2. They're all, every single one of them is sp2. So if you were to actually draw this out too, and you think about this trigonal planar, right, around each one of these bonds, this would be a nice planar molecule, the entire one. The way it's drawn out too is also giving you a bit of information regarding whether it's cis and trans. This isn't very representative in terms of actual geometry. We would actually draw out a stick figure maybe to show that a little bit better. But looking at this one, if you have both hydrogens sticking, oh sorry, that's not across the double bond. This double bond right here, okay? You have larger group attached to this carbon, larger group attached to that one, smaller, smaller. The fact that they're drawn on opposite sides of the double bond like this means that this would be trans. This end one and that end one, you don't have really an opportunity for cis or trans because it's the same thing bound to this carbon, H and H. There are no differences. Okay, now this last one, 2 different things to point out. First of all, this one here, there, and there. Those are all 4 electron group carbons. Those are all sp3 carbons. There. Now in here, each of these carbons is only bound to two other things. So carbon on this side, carbon on that side. Okay? Just because it's a triple bond doesn't mean you're adding any more to that. It's still only one area of space that's needed. So you need to mix two orbitals together in order to make those hybrid orbitals. So sp. So each of these carbons is an sp hybridized carbon.